Hello, my friends. Thank you very much for subscribing to our channel. Recalling the carpool fare sharing problem we discussed these days. If several persons take one taxi together with various distances, there can be different strategies of sharing the fare. For example, on a pro rata basis, or evenly sharing the fare generated from the distance among those who have in common. Both strategies sound reasonable, but the results can be very different. Last time, we proved that, if two persons share one taxi, when the flagged down fare of the taxi is equal to the unit price multiplied by summation of first person's distance and the distance covered by the flagged down fare, the results given by the two aforementioned sharing strategies are the same. So, what about if three persons carpool one taxi? Let's clarify the question again. The first person travels X kilometers, the second person, Y kilometers, and the third person, Z kilometers. X is not bigger than Y, and Y is not bigger than Z. The flagged down fare of the taxi is S, which also covers the first W kilometers, and W is not bigger than X. The price per kilometer after the first W kilometers is R. The first strategy of sharing the fare is according to the ratio of X to Y to Z. The results of the three persons fares are A1, A2, and A3. The second strategy of sharing the fare is that, the fare of the first X kilometers is evenly shared by all the three persons. The fare between X and Y kilometers is shared by the last two persons. And the cost between Y and Z kilometers is paid by the third person himself. The results of the three persons shares are B1, B2, and B3. The question is there any situation where A1 equals B1, A2 equals B2, and A3 equals to B3? Why not give a try, and we will come back soon. For the first extreme case, where X, Y, and Z are all equal, there's nothing to discuss, because all three persons share all the fares equally anyways. For another extreme case, where X, Y, and Z are all different, we have to make the analysis step by step. In this case, B1 is equal to S plus R times X minus W, divided by 3. B2 is bigger than B1 by half of R times Y minus X. B3 is bigger than B2 by R times Z minus Y. Because B1 plus B2 plus B3 is equal to A1 plus A2 plus A3, the case where A1 equals B1, A2 equals B2, and A3 equals to B3, is equivalent to that. The ratio of B1 to B2 to B3 is equal to that of A1 to A2 to A3, which is equal to the ratio of X to Y to Z. Let's first handle the part that B1 to B2 is equal to X to Y. That is, B1 to B2 minus B1 is equal to X to Y minus X. Namely, the ratio of 1/3 of S plus R times X minus W, to the ratio of half of R times Y minus X is equal to the ratio of X to Y minus X. Since X is not equal to Y, Y minus X can be removed. So twice S plus twice R times X minus W, equals 3 times R times X. That is, S equals half of R times X plus twice W. Bringing it into the expressions of B1 and B2, we get that, B1 equals half of R times X, and B2 equals half R times Y. In the following, we analyze the ratio of B2 to B3 equal to that of Y to Z in the same way. The ratio of B2 to B3 minus B2 is equal to that of Y to Z minus Y. That is, the ratio of half R times Y to R times Z minus Y is equal to the ratio of Y to Z minus Y. Again, because Z is not equal to Y, we get that, half Y is equal to Y. Then Y has to be 0. This is obviously impossible, so in the case where X, Y, and Z are all different, A1, A2, A3 and B1, B2, B3 cannot be the same in any case. So, what if two of X, Y, and Z are equal? For example, if Z and Y are equal, this situation will not change our first half of the calculation in the previous case. S is still equal to half of R times X plus twice W. B1 is still equal to half R times X. B2 is still equal to half R times Y. Z is equal to Y. So B3 is also equal to half R times Y, which is in fact half R times Z. The ratio of these three is indeed equal to the ratio of x to y to z. The second case is when y and x are equal. In this case, we can express both b1 and b2 as 1/3 of s plus r times y minus w. b3 is then equal to 1/3 of s plus r times y minus w, plus r times z minus y. In the same way as before, we get that s plus r times y minus w equals 3 times r times y. S is therefore equal to r times twice y plus w. Bringing it into the expressions of b1, b2, and b3, we get that b1 equals r times x, b2 equals r times y, and b3 equals r times z. Their ratio is also equal to the ratio of x to y to z. To sum up, if we want to get the same sharing results of all the three persons in both strategies of fare sharing, at least two persons' journeys should be the same. And, if only two persons' journeys are the same, the flagged down fare, unit price, and the journeys must satisfy a specific relationship. If the journeys are all different for the three person, then, no matter how to set the flagged down fare, the unit price, etc., the fare shared by them cannot keep the same if the sharing strategy changes. Then, how about if we release the requirement a little bit? We do not require that the fares shared by three persons all remain the same when we change the strategy of sharing, but only require that the fare shared by the person who travels the farthest remains the same. What will be the result? Let's continue the discussion tomorrow. Thank you for watching, and see you tomorrow.